Section 12.4 then. Composition of functions. Again, the reading assignment was good. I think that this is something that is familiar, hopefully. So we're going to prove some of the stuff in this section, not today, but we are going to make it slightly more interesting with some proofs. I want to get basic definitions today. That's what we're doing. And again, this is stuff that you should know from high school math, but we're going to make it precise. So section 12.4, function composition. Function composition. All right, here's my definition. So we are going to let f go from a to b, a function from a to b, and let g be a function from b to c. So f is going to go from a to b, g is going to go from b to c. The composition of f with g. The composition of f with g is f circle g. This is going to go from a to c. Okay, so it's going to be a new function from a to c. That's a circle. I know you can't really see the middle of the circle, but that's a circle. It's an open circle. And it is going to send an element x to f backwards g of f of x. G of f of x. Is that right? Nope, that's backwards. F of g of x, g of f of x, g of f of x. I'm thinking about this. So f goes from a to b. This is going to be an element of b. That's good because g takes as input elements of b. So this is correct. X goes to g of f of x. So that tells you in what order you have to do the functions. If you have f circle g, and this is what I asked you in your reading assignment, you do f first, and then you do g. Grant, question.
The definition in the book has it flipped, I think.
Do I have composition of g with f? Am I putting the words in the wrong order is the question.
The definition 12.5 has g circle f of x equals g f of x, like you have.
Okay, one sec. Page.
My page is different, so
yeah, you're not helpful on page numbers. G circle f, g of f of x. Composition of f with g. Oh yeah, I've got my left hand side backwards. That's why I'm having issues here. Left hand side is backwards. So the wording is correct and the right hand side is correct. I just have my side backwards here. So this is g circle f. Thank you. All good. So what we need for this to work is the codomain of f to equal the domain of g. That's what we need in order for this to work out. We need the codomain of f to equal the domain of g. Codomain of f right up here to equal the domain of g. That's what needs to happen. You can also do f circle g, right? So you could do f circle g. If you do f circle g of x, then that would be f of g of x, assuming that your functions are mapping in the right spot. Assuming that your functions are mapping in the right spot. You can do f circle g of x also. You just have to have different domains and codomains. Okay, 1, 2, 3 examples. We're probably not gonna do all 3 examples. Example number 1 with ordered pairs, and then example number 2 with the rule. And I think example number 2 with the rule is going to be super, super easy. So let's do example number 2 with the rule first. F goes from the real numbers to the real numbers. I'm going to send x to 4x squared plus 1. G also goes from the real numbers to the real numbers. And I'm going to send x to x squared minus 2. So f goes from the real numbers to the real numbers, x gets sent to 4x squared plus 1, g goes from the real numbers to the real numbers, and x gets sent to x squared minus 2. All right, so f circle g of x is f of g of x, right? That's going to be f of x squared minus 2. Do we see where that is coming from? F of x squared minus 2. That's my g of x. This is high school math. I promise this is not hard. We're doing okay here. Yes. And so then you take the x squared plus 2, plug it into x, or plug into f wherever you see an x. So this is 4x squared minus 2 quantity squared plus 1. 4 times x squared minus 2 quantity squared plus 1. Give me a thumbs up. Tell me you remember your high school math and that you can do this. Okay, cool. Do G circle F for me, please. I'll write it out without talking. Do G circle F for me. Four x squared plus 1, quantity squared minus 2. Yes, good, happy, easy, all good. Okay, notice that these are not equal, right? If you simplified out, these would not be equal, not equal. So in general, F circle G does not equal G circle F. Sometimes, if you have special functions, they can, but in general, it's not true. So in general, we would say that function composition, that's circle, right? Function composition is not commutative. If you can switch the order around, that's commutative. Function composition, circle, is not commutative. There are special cases where it is, but in general, function composition is not commutative. Okay, let's do one with ordered pairs. One more, last example for today, and then we've got one theorem to do. So my set A is going to be 5, 6, 8. B is going to be the set 0, 1. And C is going to be the set 1, 2, 3. A is 5, 6, 8. B is 0, 1. And C is 1, 2, 3. F is going to go from A to B. And F is going to be given by 5, 1, 6, 0, 8, 1. So I'm writing F as ordered pairs. We haven't done as much with this, but we'll do it right now. F is 5, 1, 6, 0, 8, 1. G is going to go from B to C. And G is going to be 0, 1, 1, 3. So 0, 1, 1, 3. Again, G can be given by ordered pairs. So my inputs to G are 0 and 1. F circle G is then going to go, nope, sorry, G circle F. I need G circle F in this case. So G circle F. Why did I pause my screen sharing? Okay, I don't know what just happened. I got a message that said your screen sharing is paused. Okay, I think we're good. G circle F is going to go from A to C. So G circle F, if it's going from A to C, 5 needs to get sent to something, 6 needs to get sent to something, and 8 needs to get sent to something. Yes? If I'm going from A to C, 5 needs to get sent to something, 6 needs to get sent to something, and 8 needs to get sent to something. G circle F means that I do F first, and then I do G. So 5 gets sent to 1, and then 1 gets sent to 3, which means that ultimately 5 gets sent to 3. One more time. 5 gets sent to 1, and then 1 gets sent to 3, so ultimately 5 gets sent to 3. Do we see where that's coming from? Ultimately 5 gets sent to 3. You're nodding at me, good. Okay, 6 gets sent to 0, 0 gets sent to 1, so ultimately 6 gets sent to 1. Last, 8 gets sent to 1, 1 gets sent to 3, so ultimately 8 gets sent to 3. This should be easy too, hopefully. Easy? Grant, question.
What happens if there's some reason like it was order pair 8, 2 in this example? Like what happens if the Y component or the B component doesn't match up with the B component?
Yep, And this is why we absolutely positively have to have the codomain of F and the domain of G equaling each other, because otherwise we could totally have the problem that you described. The Y component here not matching up with the X component here. So that's the reason for the question that you asked. Does that make sense?
Yeah.
Okay. Other questions? Same process with an arrow diagram. I won't bother to do one, but it's the exact same process with an arrow diagram. You just kind of squish. So you've got the F arrows over here. You've got the arrows in the middle, and then you've got arrows on the end, and you just kind of squish them together. You eliminate that middle set of points. Exactly the same as with an arrow diagram. Easy? Good? Okay. One theorem, theorem 12.1. And then next time we're going to do theorem 12.2, which is a little bit more interesting. So my theorem 12.1 is that function composition is associative. Function composition is associative. In other words, associative means you can move parentheses around, right? I've told you my trick of how I remember this. Associative is who you associate with, and you can associate with different people, so you can move parentheses around. So in other words, H circle G and then circle F is equal to H circle G circle F. As long as we don't run into the problem that Grant just described, as long as we have all our domains and codomains matching up where they need to be. So as long as everything is defined. So I can move my set of parentheses around. I can do function composition in either order. It doesn't matter where I start using function composition. Parentheses can get moved around. Okay. Questions on any of that? If we were in class, class would be longer because I would have made you do some of these with partners and it would have taken a little bit longer. But any questions on any of that with function composition? Okay, Friday then, we're gonna do proofs. I'm very excited about this. So we haven't proved a theorem in a good long time. We're going to prove a couple of theorems on Friday. And what we're gonna do is link function composition, 12.4, with injective and surjective from 12.2. So we're going to prove a couple of theorems dealing with function composition, injective, surjective, all that fun stuff. That is Friday. And then we will also finish up the chapter on Friday with 12.5, which is, inverse functions. Inverse functions are not hard. That's where you just switch the y and the x and then you solve for x in terms of y, right? Inverse functions, high school stuff, no big deal there. So that's why we'll do the end of 12.4 and also 12.5 on Friday. It won't take super long. Going once, going twice. Last call for anything else for other questions. Okay. Then I'll send out homework, I'll send out a reading assignment on 12.5, and I will see you on Friday. Thank you. Have a good day. Enjoy the rain. Bye.